Okay, so in this video we're going to talk about strategies for finding limits that may look like you can't direct substitute in the beginning, but with a little bit of algebra you actually can. So these are functions that agree at all but one point. We talked earlier about rational functions that might have a denominator equal to 0 if you plug the c in by direct substitution. So this is going to be a technique that you can use for some of these cases to actually be able to evaluate the limit by direct substitution. So if c is a real number and f of x is equal to g of x for all x not equal to c in an open interval containing c, if the limit of g of x as x approaches c exists, then the limit of f of x also exists, and the limits are the same. So one common version of this is what's called the dividing out technique. So when direct substitution gives you an indeterminate form, such as 0 divided by 0, you can use this technique to help you evaluate the limit. Now, if a function, when you plug in a value, gives you 0 divided by 0, this means that the numerator and the denominator of the function have to share a factor. That's why you're getting 0 on both the top and the bottom. So you could be able to divide it out. Now this doesn't mean that the function has to exist at whatever the point is. In fact, it doesn't. This is one of those cases where you can remove the problem somehow though. So let's look at that example from 1.2. The limit as x approaches 1 of x cubed divided by x minus 1. And one thing that may come in handy with some of these problems is to remember some of the factoring rules for cubes. So the difference of cubes, a cubed minus b cubed, factors to be a minus b times a squared plus ab plus b squared. And a cubed plus b cubed factors to be a plus b times a squared minus ab plus b squared. Okay, so let's take a look at this example. We've got the limit as x approaches 1 of x cubed minus 1 divided by x minus 1. So I'm going to write out what I'm starting with. And I will observe that x cubed minus 1 is x cubed minus 1 cubed, because 1 cubed would be 1. So this factors to be x minus 1 times x squared plus x plus 1 divided by x minus 1. And since the numerator and the denominator share a factor, I can cancel that x minus 1, which will be the limit as x approaches 1 of x squared plus x plus 1. And now this is just a polynomial, so I can go ahead and direct substitute. So I'm going to plug in the 1. And this gives me 1 plus 1 plus 1, which is 3. And that is the answer we got in section 1.2 when we did this numerically and graphically, and you can see it analytically here as well. Now here's one very important thing that I want you to recognize about the work on this problem. I am very particular about notation. Notation is very important because when you pick up your work, or when you pick up your work and look at your notes, you want to be able to understand exactly what you did to get from point A to point B. You would want anybody else who picks up your notes to also be able to understand. So notation is very important, and I'm a little bit of a stickler about it. One thing that you want to pay attention to is that I did not drop the limit notation. So do not drop the limit as x approaches c part of this until you actually plug in c. From here, the limit as x approaches c, the only place where I actually drop the limit as x approaches 1 is once I've actually plugged the 1 in. So that's just kind of a little warning. I do count off for that, so if you're taking one of my tests, you want to be careful about that. Another example here, we've got the limit as x approaches negative 4 of x squared plus 9x plus 20 over x squared plus 2x minus 8. If you plug negative 4 into the top, you get a 0. On the bottom, you also get a 0. So we're going to factor both of these, and I'm just going to kind of come off to the side and do some scratch work. Just a little review of factoring. I like to do the AC method. So my AC for the first one would be 1 times 20. Yeah, I'll cut this out. So this is going to factor to be x plus 4 times x plus 5 on the top, divided by x minus 2 times x plus 4. And you can see the factor that causes the problem is the x plus 4, because if you plug in a negative 4 to both of those, you get a 0. Well, thankfully we have one on the top and on the bottom, so we can cancel it. So this is now the limit as x approaches negative 4 of x plus 5 divided by x minus 2. And now we don't have a problem, so this is negative 4 plus 5. Again, I'm plugging in the number now so I can drop the limit, divided by negative 4 minus 2, which is 1 divided by negative 6, or negative 1/6. And that is your answer. Another technique is what's called the rationalizing technique. In some cases, rationalizing the numerator of a rational expression can help you to evaluate the limit. So for example, if I wanted to evaluate the limit as x approaches 0 of the square root of x plus 1 minus 1 divided by x, this would give you 1 minus 1, which is 0, and this would obviously give you 0. So this is a good candidate for this method. So I want to rationalize the numerator. So what that means is I'm going to multiply the top and the bottom by the conjugate of the numerator, or denominator, it just depends on what your problem is. And in this case, this is the square root of x plus 1 minus 1, so I'm going to multiply by the square root of x plus 1 plus 1. And if I do that to the top of the expression, I have to do it to the bottom as well. So I basically have multiplied by a 1. There's nothing wrong with doing this. Okay, so keeping my limit notation, this is a sum and difference of the same a and b, so this ends up being the square root of x plus 1 squared minus 1 squared. Now I'm not going to actually distribute this x. You'll see why in a minute. It'll actually make your life a little bit easier if you don't distribute it. Just trust me on that one for now. So what ends up happening is I get x plus 1 minus 1 divided by x times the square root of x plus 1 plus 1. And that is the limit as x approaches 0 of x divided by x times x square root of x plus 1 plus 1. Now because we didn't distribute that x, we can just cancel it here. So this is the limit as x approaches 0 of 1 divided by the square root of x plus 1 plus 1. And now that we are actually plugging in the x equals 0, we can drop that notation. So this is 1 divided by the square root of 0 plus 1 plus 1, or 1 divided by the square root of 1 plus 1, which is 1 over 1 plus 1, which is 1/2. So that is my final answer. Very similar problem. If you tried to plug in a 3 to this, you would get the square root of 4, which is 2, minus 2, which is 0, over 3 minus 3, which is 0. So we would want to multiply this by the square root of x plus 1 plus 2, and we're going to do that on the top and the bottom. So that'll be the limit as x approaches 3 of x plus 1 minus 4 divided by x minus 3 times the square root of x plus 1 plus 2, which is the limit as x approaches 3 of x minus 3 divided by x minus 3 times the square root of x plus 1 plus 2. So I'm just doing some algebra to simplify this. And now you can see that the x minus 3 cancels. So I have the limit as x approaches 3 of 1 over the square root of x plus 1 plus 2. Now that I'm plugging in the actual 3, I can drop that notation. So that's 1 over the square root of 3 plus 1 plus 2, which is 1 over the square root of 4 plus 2, which is 1 over 2 plus 2, which is 1 over 4. And that is my answer.